Welcome to this video about the possibilities that Mechatronics provides for the robotic machining of metal and composite parts. This presentation was made public at the Basque Industry 4.0 Congress in Bilbao, Spain, on November 2018. Machining is a pillar of the European manufacturing industry. Aluminum and composite parts can be machined with robots, including milling, drilling, and trimming operations, since cutting forces in aluminum and composites are way lower than in other materials such as steel or titanium. Compared to a machine tool, the economic investment required to set up a robot for machining is lower. Robots don't require much space in the factory plant, while their working volume is significant. Robots can also perform additional operations, such as part pick and place or non-destructive testing. Unfortunately, robots have two big limitations. Their accuracy is not as good as the accuracy of machine tools, and the same goes to the stiffness. This is an example of the accuracy of a heavy industrial robot. The data has been provided by the robot manufacturer itself based on a calibration performed at the manufacturer's facilities before shipping the robot to the end user. The calibration was done without any payload on the robot, while in a machining application we could expect the robot to have a spindle between 10 and 30 kilograms, which would affect the accuracy negatively. It can be seen that the mean precision in the whole workspace is 0.13 millimeters, but at certain point it drops down to even 0.21 millimeters. If we consider a volume of under 1 cubic meter in front of the robot as a high precision area for the robot, even in this situation, the precision is around 70 microns, but it can get even to 120 microns at some points. In order to make an analysis of the overall performance of a machining robot, an aluminum part has been machined according to ISO 10791 standard. This standard is called Test Conditions for Machining Centers and is based in the American National Aerospace Standard 979, which determines the geometry tolerances of a part including circle, square, diamond, and hole features that a machine tool should be able to perform. The material of the part is aluminum 7075T6, which is highly used in the aerospace industry. The cutting conditions, axial and radial depth of cut, spindle speed, and tool feed, among others, were adjusted as required by the standard. The machining was performed at IDECO's Research Center Robotic Machining Cell, which is formed by an Staubli TX200 robot, a high spindle speed, automatic tool changer, and rotary table. Indeed, this robot is part of the Basque Digital Innovation Hub on Flexible Robotics and is available for companies to perform research activities on it. These figures show the machining process and the final machine part. In the following video, we will see how the machining was performed in accelerated time. This is the part that was machined with the robot, and a coordinate measuring machine was used to analyze the geometry of the machine part. As expected, the results were out of the admitted tolerances for a machine tool. Only 1 out of 22 parameters was inside the tolerance, and the mean deviation was 500%, which is very significant. The test proves that it is not possible to use a right-out-of-the-box robot with cutting conditions coming from the machine tool industry and obtain acceptable quality parts. It's clear that specific actions are required to improve the performance of robotic machining. Here's where we have an opportunity for Mechatronics to improve the situation. Indeed, the absolute accuracy of the robot must be increased. It's necessary to compensate the robot deformation suffered due to the cutting forces during the machining. And indeed, the cutting forces themselves should be minimized, and it's necessary to monitor the amplitude of the vibrations during the process. Out of this range of possible mechatronic concepts, a multi-camera system is proposed to improve the absolute accuracy of the robot. The multi-camera system is based in photogrammetry. Markers are placed on the robot and they are localized using cameras. It is a low-cost solution compared to other systems using laser tracker technology. It has been patented and validated in the machine tool industry for the machining of large parts. This is an example video of the multi-camera system making the localization of the part, fitting the real part and the theoretical part, and automatically generating the frames for machine and part referencing. The accuracy reached in this application is 50 microns plus 20 microns per meter. It has been developed in collaboration between Solaluce machine tool manufacturer and IDECO Research Center. These are the artificial markers which are placed in the part, in this case, in the case of the use of this system in the machine tool industry. And with the cameras, it's possible to take the pictures of the markers, and then the system will automatically find where the part is. These are two example videos of the application of this multi-camera technology in robotics. In this case, the cameras are locating the part and they are helping the system to make an assembly. In this other scenario, the robot was used as an assistant for a human to make some assemblies manually. The robot, here we have the robot, you can see the markers, and the robot pushes a part until a certain position, which should be pretty accurate. This is where the multi-camera system works, and the human then makes the positioning of the parts that must be assembled with the assistance of the robot. Currently, in a workspace volume of 1 cubic meter, an accuracy of 45 microns has been reached. One position correction is done every second using Wi-Fi connected cameras. This performance makes the system applicable in drilling operations if we are taking it to the machining application. In the near future, improvements in accuracy are expected. In 1 cubic meter, the objective is to reach 30 microns. In 8 cubic meters, 60 microns, and 100 microns in 18 cubic meters. The use of field buses and high-speed processing could lead to 20 position corrections per second. This will make the system ready for milling applications. A second mechatronic system to increase the accuracy of robot machining is based on the identification of the stiffness of the joints of the robot. 80% of the deflection suffered by the robot under load forces is originated at the robot joints. The Cartesian stiffness on the tool center point changes depending on the robot position and orientation. In an extended position, the Cartesian stiffness of the robot is lower than when the robot is retracted. On the opposite, the torsional stiffness of the joints remains constant, since it is related mainly to the gears of the joints. If we knew the stiffness for the joints, the Cartesian stiffness on the tool center point could be calculated for any robot position and orientation. Once the Cartesian stiffness is known, the robot deflection can be corrected by measuring the force in real time or predicting the force in simulation. In Coroma project, several devices are under development to identify the stiffness of the joints. These systems are based on accurately measuring the deformation of the robot under different external forces. We can see a video where the device is being used to identify the deflection and the forces in the robot in order to make the calculation of the stiffness of each joint of the robot. Up to 93% of the errors have been predicted during calibration tests. In machining conditions, the compensation may reach up to 80% of the deflection. A CEN workshop is underway as a first step to set a feature standard in good practices. The name of this workshop is Articulated Industrial Robots, Electrostatic Compliance Calibration, and any industry or research organization which would be interested in participating in this workshop is open to contribute and participate in it. We have seen how the stiffness can be identified in order to predict the deformation, but it is also important to minimize the deformations by optimizing the cutting conditions. Using cutting force simulation, it is possible to optimize the milling and drilling operations with the objective of reducing the amplitude of the forces, since smaller forces produce smaller deformations in the robot. In the pictures, you can see some of the marks left in an aluminum part related to the deformation in the robot while it was machining. Going back to the aluminum part previously mentioned, machined according to the ISO 10791 standard, it is possible to significantly reduce the cutting forces. Modifying the axial depth of cut, spindle speed, and robot feed, the machining productivity can be maintained while the forces can be reduced in 61%. You can see here how certain values have been modified and we have obtained a significant reduction in the forces while the productivity has been maintained. Finally, it is also necessary to monitor and suppress high-frequency vibrations in robotic machining. Aluminum and composite parts are machined using high spindle speed. This leads to high-frequency vibrations that can significantly reduce the quality of the machine surface. Regenerative chatter vibrations are especially harmful since they can bring the machining process into an unstable situation, creating very bad quality surface in the part. It is very important to notice that the origin of these high-frequency vibrations is not in the robot structure, but usually on the tool or the part itself. This is a key aspect which must be taken into account. Since the stiffness of the robot is lower than in machine tools, it's not uncommon to relate vibrations in the part to the stiffness of the robot structure, which would be a mistake, since the origin of the vibration is not in the robot, but it's in the tool or in the part. Several systems have been developed by Coroma project partners to continuously monitor the robot and the machining process using local and cloud-based architectures. A combination of automatic detection of high-frequency regenerative vibrations and techniques for automatically suppress these vibrations have proven to provide very good results. This is based on automatically tuning the spindle speed based on the measured vibration sensor signals. A continuous learning module has been developed to identify the successful machinings and the troublesome machinings where vibrations are present, based on machine learning, in order to provide cognitive and reasoning capabilities to the robot to select optimum cutting conditions that prevent vibrations. This is an example of frequency analysis of a machining operation. On the left figure, you can notice a high frequency vibration around 6,000 Hz. The vibration was automatically detected by the system and the spindle speed was modified, as you can see on the right figure, removing the vibration. Summarizing, we have seen 4 different mechatronic technologies that can improve the performance of robots in the machining of aluminum and composite parts. A multi-camera system to improve the absolute robot accuracy, a system for the identification of the stiffness of the robot joints and predict deformation in the robot during machining in order to compensate these deformations, the possibility of optimizing the cutting conditions to minimize the cutting forces and therefore minimize the robot deflection, and the monitoring and suppression of high-frequency vibrations to obtain a better surface quality. Thank you very much for your attention. If you are interested in robotic machining and mechatronics for robotics, feel free to visit Coroma project website or directly contact me by email.